we're going to talk about some very special exponentials and logarithms, specifically base e, e to the x and log base e of x. Now, e is a pretty special number. Here are three definitions. It's the limit of 1 plus 1 over n to the nth power. If we go back to our compound interest formula, this shows up in the continuous compounding. We'll see that right here. And so it's a limit. So imagine, okay, basically what happens here, if you take $1 and interest rated at 100% for n compoundings per year, depending on how many compoundings it is, you'll get a different value. If it's just one compounding, it doubles in a year. If it's 4 compoundings, it's 1 1/4 to the 4th power. If it's 12 compoundings, it's 1 1/12 to the 12th power, and so on. And the limit is a number e, which is approximately 2.71828182845.9. It goes on forever. It doesn't repeat. It's an irrational number. It's a pretty basic constant in mathematics, in some sense as basic as pi, but actually we've only known about it for a few centuries, as opposed to pi, which we've known about for millennia. It has this very interesting formula. It equals 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4 plus, and so on like that forever. This is called an infinite series. It converges quite quickly to this value. Now, okay, I was saying about continuous compounding. Before, we had compound interest formula where we had the p is the present value, a is the later or future value, t is the time, r is the interest rate, and we also had k for the number of compoundings per year. But if we let k go to infinity, so it's compounding all the time and therefore continuous compounding, you get this formula. A equals p times e to the rt. PERT. All right. ln of x is log base e of x. It's called the natural logarithm for reasons I'll explain in a few moments. Natural log of e to the x is e to the natural log of x equals x. E to the x grows exponentially. It's an exponential explosion because 2.7 is bigger than 1. Starts small, gets big. Flip it through the diagonal, get this graph here, ln of x. It goes to infinity near 0. At 1, it equals 0. At e, it equals 1, and so on. Now, the name natural logarithm comes from this interesting fact from calculus. Take this graph, y equals 1 over x, the hyperbola, and draw this line, vertical line at x equals 1, and this vertical line at x equals k, and get this four-sided figure bounded by 3 straight lines and the curve 1 over x. This has an area, and the area is the natural log of k. And you can see how as k goes, move k out, ln gets bigger ever slower and slower. And it's because of this relation is why it's called natural, because 1 over x, see it on math all the time, and the area under a curve is something you see in calculus all the time, so it just shows up quite naturally in the calculus. And therefore in all of physics and math and chemistry and so on. All right, so here's some examples. We'll use the continuous compound interest formula, a equals p e to the rt. And so, okay, we have this $15,895 interest, or principal, excuse me. It's decaying at a rate of -2%. And this goes on for 16 years, compounding continuously. What's the later amount? Okay, well, it's p e to the rt, 15,875 times e to the -0.02 times 16. And after running it through the calculator, you get 11,542.14. Here we have p equals 565 at an interest rate of -0.5% for 8 years. What's a? 565 times e to the -0.5% times 8 equals, calculator, 542.85. Here we have the natural log of the cube root of e squared. Well, the cube root of a square is a 2/3 power. This is natural log of e to the 2/3 power. Natural log is log base e. So log base e and exponential base e cancel, and we're just left with 2/3. Let's see if I get that right. Oh, I'm sorry. All right. ln of x is 4.24 for what x? Well, you transpose the log base e to an exponential base e. So x equals e to the 4.24 and run into the calculator 69.4079. I suppose I should say that at least in this calculator here, you can see e to the x. There's this ln button right here, and you push the second function button, and yellow right above it is e to the x. So that's how you can do this on a calculator. And I'm pretty sure that if your phone does a calculator, so many of you will have a calculator on your phone like this, and let's see, yeah, here's a calculator button, and here's this simple 4-function button. But if, at least in this machine, when you turn it sideways, you get a scientific calculator, and it definitely has ln and e to the x. So it might be available on yours. Here we have ln of x is negative 3.71. So what's x? Well, transpose the natural log, get exponential base e. X is e to the negative 3.71, which is about 0.0245. Now here we have a compound interest problem. $5,000 is invested at 8.2% compounded continuously. I wish I could get rates like that. For 12 years, I wish I could get rates like that for that period of time, and you'll see why in a few moments. $5,000 times e to the 0.082% times 12 equals, churn, $13,375.68. It more than doubled, almost tripled in those 12 years. Not bad at all. That's 73. All right. 5. All right, this is a simple calculator problem. You have a $2 increasing at 27% for 12 years. How much? 2 times e to the 0.27 times 12 comes to 51. Okay, that was pretty routine. Okay. Let me stop this.